Hello AP Chem students and welcome to topic 3.9, separation of solutions and mixtures. The learning objective here is 3.9.a, explain the results of a separation experiment based on intermolecular interactions. So let's get into it. Okay, so let's first talk about why we're talking about separation techniques. So often in chemistry, mixtures are encountered, and it's common for chemists to want to separate those mixtures into their components. And by the way, this is not limited to chemistry. This is exactly the same thing as what happens if you, for example, make coffee or tea. You separate the mixture of the dissolved coffee from the coffee grounds, or you separate the mixture of the dissolved tea from the tea leaves. So we can take advantage of the fact that the components of the mixtures have different physical or chemical properties and the difference in these properties based on the substances. And that dictates what technique will be used for separation. So we look at the differences in the properties and then we decide what separation technique we'll use. So we're just going to get straight into it. And some of these will be familiar to you. So the first one we're going to talk about is decanting. And when you have decanting, you carefully pour off a layer that's on top of another separated layer. Now, this can look at a couple different things. So a really common one is if you have a liquid, you have an undissolved solid, you might pour off the liquid and leave behind the solid. And you could be collecting either one here. Maybe you're trying to collect the solid or maybe you're trying to collect the liquid. You can also have a situation where you're separating a mixture of liquids. And this is called a separation funnel or separation flask here, filter flask. And so what you can do here is you turn the stopcock and you would pull, or you would let one layer flow through, and then you would try and stop it before you get the next layer, and so on and so forth. So the property difference that's exploited here is density, IMFs or polarity, and states of matter. And then this might be what a particle view looks like. So they're in two separate layers. Now, you probably understand this already, but this is not a very precise method of separating. So often we would put decanting with something else. So for example, if we are producing a precipitate and we want to collect the precipitate, we might decant off the top layer of liquid if there's a lot of liquid on top, and then follow it up with another method to separate. And so the method we followed up with is likely not going to be this one, but we'll talk about the other method in a second. So distillation is a process in which a mixture is heated, okay, until one pure substance boils, and that substance is then cooled, condensed, and collected. So you can see, I've got two illustrations for you here. So you have a substance in a flask, you heat it up, one of the substances vaporizes, and then it travels into a tube, and then surrounding the tube, and this is better shown over here, there's cold water that goes into what's called a condenser. Now, this is a tube within a tube, the condenser. So cold water is surrounding the inner tube, but not coming into contact with the gas that's in there. And then by cooling it down, then the gas that you vaporized recondenses. And then this is, of course, slanted, and then you can collect that at the end, as you can see in this nice little animation here. So the property difference we're taking advantage here is different boiling points. And it's important to keep in mind that the substance with the lowest intermolecular forces will be collected first. And if you need a review on that, you can go back in Unit 3 to, let's see, topic 3.3, solids, liquids, and gases. That's where we talked about that, I believe. We might have also talked about it in topic 3.2, properties of solids. Okay, so then a particle view would look like this. So you have this mixture, and then the orange, in this case triangles, gets enough energy that those particles will escape the surface of the liquid, become a gas, and then they can be recondensed and collected. So when I was talking a minute ago about you might want to partner decanting with something else, filtration is the something else that you might want to partner it with. So this is possibly more familiar to you in the examples that I mentioned up front with making coffee or making tea. So with filtration, a mixture is usually goes like this. A mixture is poured into a funnel. The funnel has filter paper inside of it. Sometimes the funnel itself is the filter, but more often we line it with filter paper because it makes it easier, to collect the solid. The liquid and smaller particles, depending on the size of the filter paper, will pass through the filter, while the larger particles remain trapped in the filter. So it looks like this, right? So here's what's called your residue. There's your filter paper. You pour your mixture in there, and then you just allow gravity to do its thing, or you can do a vacuum filtration, which is where you would hook this up to some sort of vacuum source, be that a vacuum pump, or it could be an aspiration system where you hook it up to the sidearm of a water tap where water is flowing past quickly, and that creates a vacuum. Here's another example of this situation. So the property differences that are exploited here are particle size, solubility, and states of matter. So if you have something that is fully soluble in water, it will not come out by filtration. You would have to distill that or do some other kind of collection. So something that is fully soluble will pass on through the filter paper with the water. But if you have something that is insoluble, then filtration is a good choice. Filtration is also can take advantage of different particle sizes, particularly if you do a filtration where you've got different layers of something that might have different sizes. For example, they take advantage of this during water treatment plants. They might have a layer of gravel, and then underneath that, they might have a layer of sand. And so then, the different sizes would be filtered out at different levels of that filtration. Okay, and so this is what a particle view diet illustration might look like here. So if this is your filter paper illustration in the purple, and then the black dots would be the water passing through, whereas the blue dots would be, like if we're looking at this example here, might be the chalk pieces. All right, chromatography. So chromatography has several different kinds. Most often in AP Chemistry, we look at paper chromatography, but we're going to talk about it in general right now because they all follow the same principles. So you have a dot of a sample, or sometimes a solution itself is just poured in the case of column chromatography. But with paper chromatography and thin layer, you take a dot of your sample and you place it on the stationary phase, and it's a small dot. So you might use a toothpick or a capillary tube to put it on your stationary phase, which could be something as simple as filter paper or chromatography paper. The solvent, which is the mobile phase, is then allowed to wick up your stationary phase. So if it's paper, you would usually put it down inside a beaker, and then the solvent would move up. So the sample moves with the solvent if it's attracted to the solvent, or it is slowed if it's more attracted to the stationary phase. So this is what this looks like. So here's your solvent. The paper is allowed to be down in the solvent, and then your spots are moving slower or faster based on the amount of attraction they have for the solvent versus the paper. So you're taking advantage of polarity and IMFs in general here because of the attraction for the media. So this relates to solubility, which is topic 3.10, which is actually the next video that I'll be posting. So if this is something that you're a little fuzzy on, hang on for topic 3.10. But here's a particle view illustration. I've actually got this zooming in. So here you have a paper, and then in this case, you have a more polar and nonpolar mixture. And then the more polar molecule will spend most of its time in the polar solvent, and the more nonpolar molecule will spend most of its time in the nonpolar solvent. So this is a little more complex than we often see because you have a mixture of solvents here. But in this case, the paper itself is a little bit polar, and so the polar solvent will not travel as far, and the nonpolar solvent will travel farther. And so you can see that here. They're illustrating that with these OH groups. And so the polar solvent moves a bit slower because it's more attracted to the paper, and so the more polar spot will move slower. So basically, you want to read in the problem to see if the surface is polar or nonpolar, and if the solvent is polar or nonpolar. And sometimes that's a relative judgment. Like cellulose paper is going to be slightly polar, and so then you have to think about, is your solvent more polar than your cellulose or less polar than your cellulose? Okay, so while paper chromatography is the most common in the AP classroom, there are other types of chromatography that you'll encounter. This title should actually be other types of chromatography. So here's column chromatography, which I was talking about. You would pour the whole sample, and then this is your sample, and then this is your stationary phase, and then your sample would separate. You would put a mobile phase on top. And then your sample would separate based on the attraction it has for the stationary phase or the mobile phase. And so that would look like this. And then you kind of come out in bands or different fractions of molecules based on how attracted they are to the stationary or the mobile. The advantage of column chromatography is that you can collect the different components at the end and do further chemistry with them. Thin layer chromatography is something you see really often, especially in organic labs. And so it's very, very similar to paper chromatography. It's just a bit more advanced, and you use something called a thin layer chromatography plate, which is usually got some kind of silicon on it. So, okay, moving forward. So then we can do calculations with chromatography, and that calculation is called a retention factor, which is RF. So when we're examining paper or thin layer chromatograms, the retention factor is used to analyze the data from different trials so that comparisons can be made. And so we calculate it in this way. So RF is the distance traveled by the analyte over the distance traveled by the solvent. And so this is a ratio, and that is important because if we're doing different trials, the solvent is not always going to move the same distance between trial 1, trial 2, and trial 3, for example. However, the RF factor is going to stay the same if you have the same unknown, okay? So it doesn't matter how far your solvent travels, you can do this ratio, and you know that that ratio is what you can match. So please do not compare the distance that the spot travels directly. You can only compare the RF values directly. So it's really important that you remember that. Okay, so this is how we do it. So if you have your spotting line here, which you mark on your paper and pencil, and then you got your solvent front that moves this far, and you would mark that in pencil as well, then that's the distance your solvent travels, and then this is the distance that your spot traveled. And so then you strictly divide this distance by that distance. So the part divided by the total. It's just like you would do a percent. It's part over whole. So the polarity of the analyte, the polarity of the solvent, and the surface, all of these impact your RF. Okay, so the intermolecular forces that are at play. So here's another example where we're looking at different RF factors. So here, if your solvent front traveled this far, this went 1.5 centimeters. This would have an RF of 0.15. So this must have traveled 10 centimeters. This would have an RF of 0.3, and this would have an RF of 0.7. But if you have something else, if you do another trial, and in that case your solvent only went 5 centimeters, right, then you could still, this spot, we would expect them to only go 0.75 centimeters, but your RF would remain the same. And that's really important for you to understand. So the meaning of RF value is if you have a small RF value, okay, so for example, back here, we have a small RF value over here, and we have a large RF value there. A small RF value means that the analyte did not travel far relative to the mobile phase. And so that means, I meant to delete that out. It means that your analyte is more strongly attracted to your stationary phase than your mobile phase. So their IMFs are similar. So, for example, if your stationary phase is less polar than your mobile phase, and we often see that situation, then your analyte is nonpolar or it has a small dipole moment. On the other hand, if you have a high RF, then your analyte traveled far relative to your mobile phase and is more strongly attracted to the mobile phase than the stationary phase. So that means that the IMFs are similar between the analyte and the mobile phase. So for example, if your stationary phase is more, sorry, I have this backwards, hang on. Okay, fix that. So if, in the same situation, if your stationary is less polar than your mobile phase, then in this case, the analyte is polar or is more polar because it has a higher F, therefore it's more attracted to your mobile phase and is going to move farther. So what should you be able to do with this? Great question, here you go. So choose the appropriate technique to separate a described solution or mixture. So think about particle size, think about polarity differences, IMF differences, things like that. And also think about states of matter. Calculate the RF of an analyte on a chromatogram. Remember, you would just do the distance the spot traveled over the total distance the solvent traveled. And then compare those RF values for two analytes based on the intermolecular attractions between the mixture and the mobile or stationary phase. So what we've seen there is we've seen students asked to compare spots on two different chromatograms, and they need to make sure that they're comparing the RF and not comparing that the distance traveled directly. You need to do that RF calculation. We've also seen students have to justify if a spot is more or less polar, like maybe comparing two spots, which is more or less polar, and you would do that based on your high RF or your low RF relative to the type of solvent that you have and the type of stationary thing that you have. So there you go. That is separating solutions, and I'll see you soon for topic 3.10, which is solubility.